is this is the APB 3.3 projectile fired at an angle. We just finished talking about projectiles fired horizontally. Now we're going to look at projectiles fired at an angle. Here we have a bicyclist that we're going to launch here into the bags, and we see it's a parabolic shape that he follows. Well, we're going to look at that in the from the top and from the bottom. We look at that from the front view. Look at the Y direction. So now he's going to come at us from the front direction. We're just going to be Y direction only. What it looks like is that he's moving straight up and straight down. That there is actually acceleration in the Y direction. That this person, looks like you're just tossing him up in the air and coming back down. And then the second motion we'll look at is in the X direction. Play this, we'll see that it looks like he's just moving at a constant velocity. Now, when we take those two motions together, you get the side view of what you saw originally. That's this motion. Those two motions together in the X and Y direction come up with this parabolic motion that you see here. In this picture here, somebody shoots a ball straight up in the air from the car, and it ends up landing exactly where they are in front, where it will land right back on top of them. The car is moving with a constant velocity to the right, and the rifle is pointed straight up. In the absence of air resistance, a bullet fired from the rifle had no acceleration in the horizontal direction. As a result, the bullet will land back in the barrel of the rifle as it moves along. Some features about projectile motion I want to take a look at is that we're going to shoot this projectile at a 30-degree angle. You see it lands a certain distance away. And now I want to have it land at the exact same point, but shoot at a different angle. What I would do is I would change it to 60 degrees and fire, and it would come straight up and straight down at the exact same point. If I did 20 degrees and I fired, the other angle that would be, it's complementary angles actually travel the exact same horizontal distance. Okay, they're in the air at different amounts of times, but they will travel the exact same horizontal distance. If you want to go the furthest possible distance, you set it at 45 degrees and you fire it, and that will send the projectile the furthest. The other thing I want to mention is if I change the mass, and I make it 1 kilogram instead of 10 kilograms, it's going to follow the exact same path. The mass does not change the distance it travels. The velocity will change. If I make that 75 meters per second, see that it comes out much further, lands out way out there. Okay, if I go 100 meters per second, it's going further. The other type of problem we're going to look at is when we fire from a different height. We'll see that it's more than just a full projectile. It has not only has the arc, but then the gravity goes beyond where our starting point is. And so we're going to solve problems like this as well. We're going to practice a problem here. It says a place kicker kicks a football at an angle of 40 degrees with a horizontal axis. The initial speed of the ball is 22 meters per second. Ignore air resistance and find the maximum height h that the ball attains, the time the ball is in the air, and the range of the ball. Now, we have to realize that this initial velocity is at an angle, so we have to break it up into its x-y components. So we'll do that first. The second thing we have to realize is question A, the maximum height is really only up to the top. Okay? So we're going to go ahead and solve this problem. So let's go ahead and find the maximum height of the ball. And we'll list out our givens here. Y max is what we want to solve for. The acceleration is negative 9.8 because this is a vertical direction problem. Maximum height is vertical direction. Initial velocity in the y direction is 22 meters per second times the sine of 40 because the 22 meters per second is this vector here. But we want this vector here. So we want it in the y direction. So that's why I multiply 22 times sine of 40. It's opposite of this angle. Final velocity is 0 because this is just like looking at it going up in the y direction, up here at the very top, the y direction, the final velocity at the very top of the y direction is 0. So now with these givens, we can use this equation, v squared equals bo squared plus 2a delta y, plug in our values from this list, and we end up with a maximum height of 10 meters. The second thing we want to do is find the time the ball is in the air. Now we're going to go ahead and treat this like a y direction problem again. And we have y equals BOT, which is 1 half AT squared. The delta y is 0 because it goes up, it comes back down in the y direction, and lands at the exact same height over here. So there's no change in the delta y, no change in height. It lands at the exact same height that it started, so that's why delta y is 0. Initial velocity is 14 meters per second in the y direction. We solved that earlier in the previous part of the problem. Time is what we want to solve for. And then we have 1/2 times the acceleration is negative 9.8 t squared. So we go ahead and solve for t, and we end up with 2.9 seconds for our time in the air. And the last part that we want to solve for is the distance the ball travels. And we have to find out what the velocity in the x direction is, what this velocity is real on this line. And we find that using cosine of 40 times the 22 at 17 meters per second. And we can go ahead and multiply our velocity times our time, 17 meters per second times 2.9 seconds. So we get a 49-meter distance in the x direction.